Hey programmers, Alvin here. Welcome back to our study of linked lists. So this is the second video of our linked list series. If you haven't watched the first video, you're going to want to check out that one first and then come to this video because we're going to continue with what we built last time. So on last episode, what we did was implement an iterative implementation of a singly linked list. And this time around, I want to introduce us to how we can implement a singly linked list recursively, because that's really going to open up a few different other strategies we can use as we tackle some linked list problems in the future. So our learning objective for today is to, of course, implement a recursive implementation that supports basic operations like adding a value to the linked list, printing the entirety of the linked list, as well as searching for an existing value in that linked list. And again, the constraints here are to solve all of these recursively. All right, so let's start building this together. Of course, I'm going to need my linked list class. And like we said in our first lecture, when it comes to the linked list itself, we really need to track the initial node or the head node. So on the left-hand side, it's going to be like a diagram of our currently running linked list. Of course, a linked list should start empty. And so the head pointer should just point to nothingness or emptiness, right? So for the sake of my linked list constructor, I'll just set this .head to be null, meaning there are 0 nodes inside of this particular linked list, right? Cool, so now that I have the head pointer, how can I actually insert a node into the linked list? Well, I need to actually just set that head. So now I'll want at least one method that can add nodes into my existing linked list. So I'll call it append. This append method will always add a new node to the end of the linked list, right? So if my linked list starts empty, then once I call append, it should look like this, right? It should have this .head pointing to this A node, and also A's next is set to null. So let me just satisfy that scenario, right? So I'm going to need my nifty node class, same node class as before. So just to review, in your node instances that comprise your linked list, what you're going to need to do is store some value as well as a pointer to the next node sequentially in the list, right? So I'll initialize this .next to be null. Cool. Notice that when I create an instance of node, I should pass my created value in the constructor. Cool. So let's start building this append method. And this append method is going to be pretty straightforward when it comes to the initial insertion, right? So if I'm inserting a value for the very first time, then it's as simple as just setting this .head to be that new node. So I'll create a new node with that target value. Of course, this should only occur on the very first insertion. So how do I know if I'm doing the first insertion into my linked list? Well, then you're really just checking if this .head is null, right? If it's currently null, that means that you're adding a node for the very first time. So I'll just set this .head to be that new node. Cool. So that handles my initial addition into my linked list. But of course, now I'm interested in what happens in the generic case, right? What happens when I add things like B and C into my linked list, right? I know they're going to be kind of handled in different ways compared to my initial insertion, right? So let's come up with some code that implements the generic append for my linked list. And I do want to solve this recursively, of course. I'm going to have to get a little creative over here. So I know that if I want to translate iterative code into recursive code, that means I can't be using any loops. Instead of having multiple loop iterations, those iterations kind of translate into multiple recursive calls, right? So I think a nice way to kind of divide and conquer this one is to maybe create like a helper function. So when it comes to my top level API for my linked list, I do want to follow and make sure that my append method has the classic signature where I just have to pass in the value that I want to create. But for the inside of my linked list, I'm going to also need a helper function. So I'll call it _append. It's still going to take in my created value, but it's also going to take in the current node that it's kind of at right now. I'm going to track the current node recursively. So what I'm saying here is this method that starts with an underscore, no one should really call this method if you're on the outside of the class. This is only for the sake of implementing append recursively, right? So I'm going to basically be using this as a helper function. So in this recursive function, let's start with the base case. So the base case for adding a new node to the end of my linked list really occurs once you're at the end of the linked list, because then you can just insert your node right there. So how can I check, if I'm at the end of my linked list? You're really just asking if you're at the tail, right? So I can check, hey, if my current node's next is null, then that must mean you're at the very end of your linked list, right? So in other words, if this is my current linked list containing A, B, C, and I wanted to insert D at the very end, then I just have to make sure that cur is pointing to C, right? Because C's next is null, which means I can just do something like cur.next and assign that to my new node with that target value, right? So this is really my base case, right? So if I'm at the end of my linked list, then just set your current's next to be your new node and make sure you return, right? Every base case should not make any recursive calls. But now I have to think about my recursive case, right? Let's say I'm not quite yet at the end of my linked list, then all I need to do is call this method recursively. So I have to say this dot underscore append. I'm always going to pass in the same value, right? The value never changes. Only my current position changes. So instead of passing in cur, I just want to go to the next node recursively. So I'll just pass in cur.next. Cool. So this code is looking pretty good. This should basically mimic like the iterations through every node of my linked list in order. Of course, I need to be sure I actually call this method though. So in like my main driver method, this append, here I'll make my initial call to my recursive function. So I'll say this dot underscore append, pass in the same old value. And you're probably wondering, what should be my initial cur? Well, just like it was in the iterative code we did on last episode, just pass in this dot head. Cool. So here we have a nifty looking recursive function to add nodes to the end of my linked list. So let's run this code. If I print out list.head, that should be printing out the A node, and we can trace through things from there. So I'll run linked list. So I see that, yeah, list.head has a value of A. But if I look at the next node after A, it looks like it also has a value of A. So something's definitely a little wrong in my code. If I scroll up a little bit, so if I look at this append method, something's definitely going wrong when I do my very first node, right? When I create my first node. So this if statement checks, hey, if I'm doing the very first addition into my linked list, in which case I set this dot head to be my new node, but because I don't do a return over here, it looks like we're also going to append that node twice, right? So technically the case of the very first addition into my linked list, that's actually an edge case. So I could just return over here, or you could do like an if else statement. So that should make sure that I don't like duplicate the very first node. Let's run that. This is looking a lot better. So my initial this.head has a value of A, A's next is B, and then B's next is C over here. Cool, let's go ahead and add a D node. And then I think we should work on a nice print method. Yeah, so it looks like C's next turns into some node, but it's not going to render things all the way deeply. So why don't we work on a recursive method that just prints out the different values in order of my linked list. So I think I'll follow the same convention over here. So let's say we had a print method. It doesn't take in any arguments. Let me also give myself kind of a recursive method. So I'm just going to use this same pattern again, right? I need to pass in an additional cur argument, but I don't want like the top level user to have to deal with that argument, right? That wouldn't really be fair. So what I'll say is for this recursive method print, it just takes in my current position. So let's start with our base case. I think the nice base case to write here is you check if your current position is null. And that handles really two things, right? It could mean that you've already consumed past the end of your linked list, or it could also mean that your linked list itself is empty, in which case this dot head is null. So if my current pointer is null, then what I'll do is there's nothing really to show for, so I'll just return the empty string. So I want this print recursive method to return a string containing like the values of my linked list. So I'll return the empty string. And then in the recursive scenario, if I make it past this if statement, that means that cur is not null. So cur is most definitely an actual node, which means I can totally access this node's value, right? And I'll take that value and concatenate it with the string that represents the rest of the linked list. So when I make this recursive call to print, I'll be sure to pass in cur.next, right? That's the very key pattern when you traverse through a linked list. you want to keep setting cur to be cur.next, and this is kind of how you accomplish that recursively. Cool, so I'm hoping that my recursive method over here returns a string. In my main driver method, I'll just go ahead and maybe save that string. So I'll say const my output, and I'll set that to this dot underscore print. And how should I initially call my recursive method? Of course, you should set cur to be this dot head. So I'll pass head over here. And I'm hoping that this method returns a string, and I'll just have this print out that string, right? Nothing too crazy over here. Again, just to reiterate, the reason that I'm kind of separating the recursive code from the main function over here is just to make sure that when someone calls the print method top level, I don't want them to have to manually pass in the head, right? So let's go ahead and test this. So let me do list.print, and that should just go ahead and print out all the values for me. I'll call my main method over here. So when I run this code, I get the values A, B, C, D, because I inserted those 4 values into my linked list. Just to make it symmetric with what we did last episode, let's actually have this also show some arrows. So I'll concatenate the value followed by a little ASCII arrow over here. Cool, so now we see that A is the first node of this linked list, and D's next is null because D is in fact the tail of this linked list. So let's go ahead and trace through this code. As always, I think it's really important that you practice explaining and tracing through your exact code. For one, you're basically required to do that on your tech interviews, as well as it really helps you figure out if there are any bugs, in your code. So let's trace through how this print method works recursively together. So whenever I trace through my programs, I'm always interested in how my variables change, right? Here, it's really how my recursive arguments change. So I'm going to track a few things. Let's start by tracking the value of the cur argument. So I'm looking at this particular argument, right? So let's say we make our top level call to print. That means recursively, we're going to call our recursive method on this dot head. So that means cur is going to be this yellow arrow. It's going to be pointing at this node. So since cur is the A node, I check this if statement. I check, hey, is that node equal to null? It's not. So instead, I go into this recursive case and I take cur's value. So I take A, I'll take A over here. And what I do to it is I add an arrow, which I'll kind of exclude from this drawing. What I do is I add to it the recursive call for printing to the rest of the linked list, right? So when I call print recursively, cur, the new cur rather, is going to be my current cur's next, right? So my current cur is actually B. And notice that the thing that my recursive call returns over here, if you look at my cursor, the thing that the recursive call returns is going to be concatenated with the A. So that's why I'm drawing it over here, right? So if I look at the frame where cur is B, it also doesn't hit the base case. So I take and I return actually my cur value. So I basically return B plus some other stuff, right? Concatenated with some other stuff. And so when I make my second recursive call, that means cur is going to become C. You can already see how this pattern flows, right? This is also not the base case, so this returns C plus some other stuff. So cur is going to be D. So I'll add that string into my total return value, and things get interesting, right? So let's say I'm at the frame where D is cur. I know that's not the base case yet because the D node is not equal to null, right? So I must return D plus some other value. So I'm returning D plus the return value of this dot print on D's next. Well, D's next is null, right? There's nothing over here. And so the final recursive call just returns the empty string, which I'll kind of jot down right here. And if you look at what happens when you actually evaluate this final return statement, you're basically just adding all of these characters together. Again, in this little sketch, I've excluded the little arrow, but you can imagine they're between every pair of characters over here. Cool, so hopefully now we're getting a pretty good understanding of how to implement linked list algorithms recursively. To be complete, let's go ahead and add one more method into our linked list class, and I want, of course, a contains method. So in other words, if someone were to call the contains method, it just returns a Boolean. It tells me whether or not the current passed in value is present inside of the linked list, right? So if I look for values that I actually appended, like A, B, C, D, all of those should obviously return true. If I look for something that's not present, like let's say a z, that should just return false, right? Of course, I want to solve this one recursively. So let's start with our driver method. So we're going to do contains, same pattern as previously. And let me just start by making my call, right? So I know that I'm going to have to call my recursive method. We'll say this dot underscore contains. And I'm going to initially pass in my head, right? So this dot head over here. But now I need to work on the true work of this method. I'll define the recursive part. So I'll pass in, or I'll call this method underscore contains. And it must take in some current position as well as my target value. So over here, I should have passed in some target. I'll pass in the target followed by the head, which means that in my recursive method, it takes in still the target value as well as the current position. Cool. Nice. And what I'll do is, let me think about the base case now. So what is my base case? Well, if you've traversed all the way through your linked list and there's nothing else to look at, then I guess you're done, right? So I'll say, hey, if my current position is null, that means there's nothing else to look through. So if you get to the point where your current position is null, I guess that means that the thing you're looking for was not there because you made it through the end, right? So here I think I'll return false, right? This handles a few things, right? It means I either traversed all the way through my linked list and did not find what I was looking for, so return false. Or it could also be the case that my entire linked list is empty. So this dot head is immediately null, so just automatically return false, right? Because it's still the case that your target is nowhere to be found in that empty linked list. But now I'll think about the recursive case, right? So in the recursive case, I could have a few different scenarios, or maybe this is really just another base case, right? If I make it past this if statement, that means that cur exists, right? So if cur exists, I think the first thing I should check is actually, hey, is that current node's value the thing you're looking for, right? So if my current node's value is the same as my target, then return true. If I look at the second if statement, it really acts like another base case, but really for the affirmative scenario, right? So I have a base case if you're done looking through the entire linked list, in which case you return false. I also have another base case that says, hey, if your current position contains what you're looking for, then just immediately return true, right? There's no point of looking any further because you found the thing. But now I need my actual recursive scenario, right? So if none of these are true, then I have to keep looking through the linked list. So recursively, I'm going to call this dot contains. I'm still looking for the same value, that doesn't change, but like you guessed, instead of looking at the current node, I want to look at the next node sequentially. And how am I designing this code? I'm solving this recursively. I know that my method should always return a Boolean, right? I know that this will eventually return a Boolean, so I could just pass that up the call stack. Cool. So this code is looking pretty good. To actually tie things together, in my main method, I'll need to just return what the recursive call returns. Nice. Notice that in my test cases down below, I don't need to pass in this dot head explicitly because that's why I have this like main method and helper function design. So let's run this code. I should get 4 trues and 1 false. Let's see this. 4 trues and 1 false, and there we have it. Awesome, so I think that wraps up our recursive implementation of the linked list. I want you to notice how similar it was in kind of logical design compared to our iterative one, right? Basically, we translated those while loops into a recursive function with a suitable base case, right? Your base case is still about when your current position is null or basically right next to null, right? In the case of appending a new node. So just for fun, let's actually solve a quick little problem that utilizes either an iterative or a recursive solution, right? So let's say I had this linked list, which contains some number values. If I run this code, I want to make sure my linked list is intact, right? So I have 11, 7, 10, and 2. And let's say right now my goal was to just add up all of these values to get the total sum within this linked list. Right, so the answer here should be 30 because 30 is the sum of 11, 7, 10, and 2. Right, how can I solve this? Well, let's maybe just practice building like separate functions. So when it comes to your like data structure challenges or like interviews, sometimes they'll just give you a linked list or really the head of a linked list. So I can reference the head or the 11 node in the case of my linked list by just saying list.head. How do I know that? If I go to the linked list class up top, to get the first node, you just say this.head, right? Or list.head in my particular variable name, right? So sometimes they ask you to write a function that takes in the head of a linked list as an argument, right? So here I'll go ahead and pretend I wanted a function called like sum, and it takes in, I'll say sum list, it takes in the head of a linked list. And I want this particular call to return to me 30, right? Because the values in the linked list are 11, 7, 10, and 2. So how can I define this separate function? Well, let's start to do it. Let's define my sum list function. And it's going to take in some head to a linked list. And I'll start by just designing this algorithm iteratively. It's very basic in an iterative sense, right? Very logical. So I know that I need to basically travel through every node of the linked list. And that's code we've covered previously, right? So the key pattern for that is have some running variable that initially starts at your head and then just keeps iterating, right? So I'm going to iterate while the current node I'm at is not null. If it's not equal to null, that means you're not quite yet at the end. So if I'm not at the end, what I should do is step a little further. So I can set cur equal to cur.next. Classic iterative linked list pattern. And as I iterate from one node to the next, I want to do something with its value. So maybe what I should have done at the top of this function is create my sum variable, which I'm going to add into on every iteration, right? So as I'm at and I'm located at a current node, I'm going to take that node's value and just add it into my sum, right? So I add current.value into my sum, also updating sum. And of course, at the end of an iteration, I need to traverse to the next node. I keep doing this until I hit the end of the linked list, in which case I could just return the sum, which should contain everything I need, right? So let me just console.log the result over here. So this is really just some straightforward code. It almost looks identical to those other methods we wrote on the last episode. Things like printing out or just returning all of the values of your linked list as a string, right? So this should get back 30. Let's give it a go. So here I have a tiny JavaScript error. I can't be or reassigning into a const variable. Should have made that let. Let's run that back. Cool, and there I have my final answer of 30, right? So this code works, and it makes a whole lot of sense, right? As you travel through nodes of your linked list, just add your current node's value into your running sum. Let's also say we wanted to solve this one recursively. I'll define a very similar method, same signature, but should be implemented recursively. So I'll comment out this iterative solution. And to solve it recursively, well, let's start by just thinking about our base case. So our base case is basically going to be a translation of this kind of while loop condition, right? So I can check, hey, if you're at the end of the road, right? So that means if your current node is equal to null, then you're done, right? So here I'm calling this head, but it can basically also act as like the current pointer, right? The name doesn't matter too much here, especially if you think about this recursively, right? So if your head is null, you can basically interpret that as your list is empty, right? If your list is empty, it contains no numbers, in which case the sum of all of them must be 0, right? Because there's nothing to add up, right? 0 is like the empty sum. But let's say you made it past this if statement. Let's say head is not null. What should you do? Well, that means I have at least one node in my linked list. What I can do is return my current node's value plus the sum of the rest of the linked list. So here I can make my recursive call and say sum list passing in head.next. So to think about this one recursively, if your list is not empty, then you can just take the sum between your current node and the sum of the rest of the linked list, and that should give you the total sum. So let's go ahead and test this recursive solution. Notice how short it is, right? So I'll run this. Again, I have my iterative solution commented out, so we're just running this new version. Awesome, notice I get the correct answer over here. And notice how different these implementations look. Although they kind of show like the same narrative in our code, right? I still have the presence of like 0 as my initial sum, and I still have to travel through the entirety of my linked list. So now that we've described two different solutions for this sum list problem, let's talk about their complexities. So in terms of the time complexity for my iterative solution, you can look at this while loop. This while loop just has to travel through the entire linked list, so every node of the linked list. So if there are n nodes, then the runtime is just O of n time. For the runtime of my recursive solution, it's really the same thing, right? I'm still going to have n recursive calls. I still have a recursive call for every node of my list. So their time complexities are the same. In terms of the space complexity, if I look at my iterative solution, it actually has constant space. So it has O of 1 space, right? I don't create any arrays. I only create a fixed number of variables. If I look at the space complexity of my recursive solution, the space complexity here is going to need to include all the stack space I require. So I'm going to need to have about n stack frames of my call stack before I bottom out at my base case scenario and finally start returning. So the space complexity of this recursive solution would be O of n space. So overall, if you wanted to optimize for time and space, you would probably prefer the iterative solution. That being said, I think there's a massive value to knowing how to think about a bunch of these linked list problems recursively. For one, look how short the implementation is. Depending on future problems you might get, thinking about linked lists in this recursive way can be very, very useful, because notice that the time complexities are actually the same. So there we have it. We finished our recursive implementation of our linked list. So now that we've gone over the iterative and recursive versions, I highly, highly recommend that you study both, right? By understanding both of these ways of thinking, you can actually open up a bunch of other solutions down the line, because you never know what type of solution a problem is going to require in the future. So that's all I got for now. In the very next episode, we'll talk about deletion of a linked list.